Okay, this is part 2 of the simple harmonic motion, meaning like this is the solution to the problems. You have all these solutions on your answer key, but sometimes I try to do different approaches to solving these problems. So on page 2, where you have these graphs, we probably talked about this in class, or you have done a lab prior to the lesson, and you figure out that if you look at the position time versus the velocity time, you're going to see that there is a shift of a quarter of a cycle. Okay, and if you look at the position, which is all the way on top, and the acceleration, which is all the way at the bottom, you're going to see there is a shift of pi, or basically half a period. In other words, when the position is at maximum, the acceleration is at minimum. I mean, it's still at maximum, but negative. Okay, so it's on the other side. So the acceleration time graph and the position time graph are always flipped. Okay, the values on the y-axis here are not the same. Okay, and I'm going to show you what those values are. If you haven't, I think we're going to do that in class. So we've done that in class already, or we're going to do it. Okay, the rest is basically just a bunch of definitions. So if I'm looking at this mass hanging here, okay, equilibrium position is right there. Okay, so I'm going to think of that position as an unstretched position. So anything that away from that position, it's either stretched or compressed. So if I pull this spring to here, right, and I let it go, it kind of comes up to here. So I'm going to call this position negative A. I'm going to call this positive A. And this is 0. So you can do it the other way. You can put this as negative A and positive A. It's just that's how I'm going to do it in class this year. Okay? And I do it every year like that. Okay. Okay, so that's the definition of equilibrium position. You can read that. A restoring force is basically a force that wants to bring you back to your equilibrium. So let's just look at this object, this mass, when it's oscillating, and when it's at position A, the force is directed towards equilibrium, because when it's here, it wants to go back to here, right? So whenever it's here, it always wants to go back to this position. When it's past here, it always wants to go back towards that position. So that's why we call it a restoring force, because it always wants to restore you back towards the equilibrium position. So this force is always directed towards the origin. So now this is a spring on a flat surface, so that can oscillate around this equilibrium position. Okay, the amplitude, just like you learned in your math class, trig class, is basically, just find some markers here. Okay, it's just the maximum displacement, okay, away from equilibrium. So in this case here, the maximum displacement is that distance between my two fingers. And it should oscillate around that, but because there is damping, which is friction basically, it eventually slows down and does this funky stuff. Okay. So that's what amplitude is. And with amplitude, we just look at the positive value of of A. We don't look at the opposite side. Okay. So this is basically going to oscillate between these 2 points here, and basically this is your amplitude. So in this case, based on this picture, they're looking at right as positive. Okay, the period is basically how long it takes to do a cycle. Okay, and you learn in your math class that whenever you do trig functions, you always break your period into quarters, because the important stuff, the interesting stuff happens at the quarters, right? So if I pull this here and I let it go, when it reaches here, that's a quarter of a cycle, another quarter, 3 quarters, and back to the period. Now, the period of a pendulum, maybe I'll prove this in another video, or maybe you can just accept it. It's 2 pi square root of m over k. Okay? M being the mass that's hanging on it, and k being the constant of this spring here. So let's see if this actually makes some sense. If I hang a heavier mass on here, I have Mr. Hughes and Mr. McQuaid here watching me, so I don't know. They're trying to kind of like make me smile or whatever, but I'm not going to smile.
I do not smile.
All right, I do not smile. All right. So if I have a heavier mass, okay, whether it's heavier or lighter, the amplitude, okay, how much I pull it from the equilibrium does not affect its period. And we can try that in class and take some measurements. Now let's look at the relationship between the mass and the period. If I have a heavy mass, more mass means more inertia, which means it's going to take a longer time to get down there. It's going to take a longer time to go back. So in other words, it's more inertia means more resistance to change, right? So if it's heavy, it's going to resist more, which means it's going to take longer, okay? For the spring constant, if you take a spring with a high spring constant, a high K, in other words, it's pretty stiff, right? So when you stretch it, its reaction is quick. It wants to go back quickly because of that stiffness, right? So if K is high, right, the period is low because it reacts much quicker than a spring with a low K. So I hope that explains conceptually why the T is directly proportional to mass, or the square root of the mass, and inversely proportional to the square root of the spring constant. Okay. The frequency is just basically, so the period is how long it takes to do one cycle or one vibration. The frequency is basically how many vibrations you do per second. So it's just the reciprocal of period. And the units for frequency is in hertz, and the period, as you can see, that it's in seconds. Okay, the next thing I'm going to talk about is this angular frequency. Sometimes we call it omega. It's basically 2 pi over t. So I'm going to write the formulas here. So t equals 2 pi square root of m over k. And the frequency is 1 over 2 pi square root of k over m. You just flip that period. Okay. Okay. These are the equations that we came up with from the graphs from the lab. So this is, I can write this as A cosine omega t, right? And I'm either going to show you in class, or I've already shown you that where these formulas come from. So for people who do calculus, this is pretty straightforward. But we're going to try to do this by doing conservation of energy in class. Maybe conservation of energy and Newton's second law, combination of those two. Okay. This stuff we should have talked about already in class. So let's take a look at it quickly. Okay. When you're away from equilibrium, whether compressed or stretched, the force is always towards the equilibrium. So anywhere in here, your force is going to be in that direction because the spring wants to push back and get back to the equilibrium. Here, the force has to be in that direction, which means the acceleration is also in that direction because the direction of the force and the acceleration is the same. Now, you can see that the acceleration is less as you get closer to the equilibrium position. And the reason for that is because the force is less. The amount of compression or stretch is less. And we know that that force is directly proportional to the displacement. In other words, the amount of stretch or compression. Okay. When we are here, our speed is 0. Okay? And as we go in towards the equilibrium, we're picking up speed. And the reason for that, because whatever loss you lose in the elastic potential energy gets changed to kinetic energy. So as you go in towards the middle equilibrium position, your velocity should be increasing, and it will reach its maximum speed at the middle. That's just conservation of energy. Because in the middle here, you pretty much have no elastic potential energy, so all that energy you had when at the outside there became kinetic, so which means maximum speed. And as you go in this direction, you compress in the spring, which means now you have more elastic potential energy, which means you're losing some speed. You're getting that elastic potential energy at the expense of kinetic energy. And you get to the other end, you stop and you turn around and the cycle repeats. Okay. And here you can see that if you are in this position here, your displacement is here. Okay. If you are here, your displacement is there. You can see that the acceleration and displacement are always opposite. So that's what the graph showed us before. And this is just a bar chart representation for what I just talked about in terms of energy. Okay, so let's look at this problem. So that was a quick summary of simple harmonic motion. So for this one here, this is periodic, but it's not simple harmonic motion. In order for it to be simple harmonic motion, the restoring force has to be proportional to the displacement, which is not the case here. Now, why is the period 2.8? Well, you can figure out how long it takes to drop 10 meters. So you can just do h is half gt squared. So this is going to be 10. This is going to be another 10. So t is going to be radical 2, okay, which is about 1.4. So if you double that, you get your period, because period is when it comes back to the same place you dropped it from. Now, this problem here, I'm going to try to do differently than the way you have this in the answer key. At which point or points is the acceleration positive? Well, the acceleration is positive when the displacement is negative, right? So that should be at point D and E. Okay, and that's the justification, what I just talked about now. Okay, so I don't want to scroll here, so let's take a look. And F also, I missed F. F is here too. So the displacement is, or the position is negative in there, so which means the acceleration has to be positive. At which point or points does the car have zero velocity but non-zero net force? Now, if you recall from kinematics, you can get the velocity from a position time graph by doing the slope. So the slope here is 0, and the slope down here is 0. So the answer should be A and E. Okay? And you can also think of it like, well, at this moment here, it has to change direction. It was going in the positive direction. Now it started to go in the negative direction because the position is dropping. So we're using the old kinematics stuff. At which point or points is the net force equal to 0? Well, the net force is equal to 0 when the displacement is 0. In other words, there is no stretch, there is no compression. So that's basically at C and G. Okay? And I'm not writing down the explanations, but I'm talking about them, so you can take notes on of that. At which point or points are the acceleration, velocity, and displacement all positive? Never. And the reason for that, because position and acceleration have to always be opposite. So there is no way that they're going to be on the same side of that graph. At which point is the acceleration non-zero and opposite in sign to the position? Well, it's going to be A, B, D, E, F, and H. Okay? So for A and B, the acceleration would be negative, which is opposite to the displacement, which is positive, right? At which point or points is the velocity non-zero and opposite in sign to the acceleration? Now, let's take a look. Well, the velocity here is 0. The velocity here is just the slope of that tangent. That's negative, but the acceleration is also negative. Okay, so that's no good. Okay, the acceleration here would be 0, right? Yeah, okay. In here, the velocity is 0 because the slope of that tangent, the velocity is negative. That's the slope of that tangent. And the acceleration has to be on the other side. So D is an option, okay? While E, the velocity is 0. At F, the velocity is positive, but so is the acceleration. The acceleration is going to be on the other side. So that's no good. And G, the acceleration is 0. At H, the velocity is positive. That's the slope of that tangent there. And the acceleration is negative down there, so it's d and h. Okay. Okay. Number 2. A particle oscillates up and down in simple harmonic motion. Its height is a function, so basically its position as a function of time is shown in the diagram. At what time does time t does the particle achieve its maximum positive acceleration? So you're going to get maximum positive acceleration when your displacement is maximum and negative. So that happens here. So the maximum positive acceleration will happen at 1 second. So that's your answer. Okay, we're going to continue with the problem. So problem number 3 on page 7, it says a 2 kilogram mass is hung on a spring of spring constant 10 newtons per meter. By how many centimeters does the spring stretch? So I think we're just going to do for that part A, mg is kx when it's just hanging there. And that's going to give us mg is 20, is 10 times x. So x equals 2 meters. So this spring is not very stiff. For part B, okay, what will be the period of oscillations? Now here they're telling you it's a different mass. So it's 2 pi square root of 0.5 over 10. And if you do the math correctly, you should get about 1.4 seconds. Okay, number C, or letter C. Okay, so I'm going to do that up here because I think I'm going to need the room. Okay, this is from the non-stretched position, meaning this is not stretched and you're going to drop it. Okay, so if at 30 centimeters, it should be still above the equilibrium position, which you can find, by the way. So if you want to find the equilibrium position here, you can just do mg is kx. And you don't have to do this. So it's 15 equals 10 times x. So the equilibrium position is 1.5 meters from this place. So it's 1.5 to the equilibrium and 1.5 from the equilibrium. So that's how it's going to oscillate. It's going to oscillate so it's going to drop 3 meters, in other words. Energy will show you that it will drop 3 meters. Okay, so 30 centimeters, it's still above the equilibrium position, but that's not important to us. Maybe I'll use it to show you a different method here. So I think when it's stretching, I think we can say that mg minus kx equals ma. Okay. Now the mg is going to be 15 minus 10 times x equals 1.5 times a. And the acceleration here will be positive 8 meters per second square. Another approach that we could do is, well, this is the spring, which is long, but it would be helpful if we know the equilibrium position, and if we stretch in from the equilibrium position. So it would be something like this. This is the equilibrium position. So basically this is negative 1.5 and this is 1.5. And this is the equilibrium. So 30 centimeters, you are here. How far are you from the equilibrium? 1.2. Okay? So we can do the other formula where the acceleration is negative k over m times x, which we derived in your in class. Okay? Now here is the dangerous part about this. The x is no longer from the top, but it's just how far you are from the equilibrium position. So it's going to be negative 10 over 1.5 times, it's not 1.2, but it's negative 1.2. And if you do the math here, you should get positive 8 again. but I do not recommend it for this problem here. Okay. Number 4, it's exactly the same process. So let's look at number 5, where we're dealing with away from equilibrium, stretching or compressing. All right. So for 5, we're going to do A. We're going to find the period. So T is 2 pi square root of M over K. So I think the first thing we have to do is find K. So mg is kx. So 1 times 10 equals k times 0.15, which means k equals 66.67 newtons per meter. You just have to come in here, plug that into here, and your period should be 0.77 seconds. Okay. How far would a 7 Newton weight stretch this spring at rest? So again, we're going to do mg equals kx. Well, the mg is already given in Newton, so 7. Okay, we're looking at part B. Equals k, which we already found, times x. So in this case here, x is 10.5 centimeters. You will get 0.105 meters, and you have to change it. So 10.5 centimeters. All right, let's look at C, which is more important, or maybe the most challenging here. So we're going to stretch past the equilibrium position. We're going to stretch by 2 centimeters, which is 0.2 meters. Okay. Now, here, I think it helps to just do negative A equals negative K over M times X and call it a day. Now, this is your negative amplitude. This is your positive amplitude. This is your 0. So this is a positive 0.02 equals negative K, which is 66.67 found earlier. The mass is different, and that's a positive 0.02. And if you do the math here, you get negative 2.22 meters per second square. All right. I do not recommend that you do it with F net equals MA, but if you want to do it that way, if let's say you forgot this formula, the first thing we have to do is we have to figure out these values. Now we can do that with energy, or we can just do it with mg equals kx and figure out how far above this point we're going to, when below this, above this point and below this point we're going to be. So this is going to be 6 equals 66.67 times x. I did the math already. That's 0.09. So this is going to be negative 0.09 and positive 0.09. So if we want to do it with mg minus kx equals ma, this is just going to be 6 minus 66.67. This is what you have to be careful. The x is all the way from the non-stretch position. So all the way down here, that's going to be 0.11 equals 0.6 times a, and you should get negative 2.22 meters per second square. And earlier, I did a equals negative k over m times x, negative 66.67 over 0.6 times 0.02, and I got the same answer. Okay? I'm not going to do number 6. It's pretty similar, but what I'm going to do here is that I'm going to say, well, what happens if it's compressed by 0.02? Okay, so this x here has to be negative. Okay, so let's see how this works if we get the same answer. If I try to do it with the first method here, which I do not recommend in this case, this 0.11 will become 0.07. And if you do the math, you'll get positive 2.22. Now, there is a nice symmetry to all this. And it kind of like makes sense because the restoring force is towards here. You're trying to go back to here. So the net force is down in that direction, which means the acceleration is also in that direction. So the acceleration is positive. In here, this will be negative, and this will be positive. That's if you decide to go with compressed. Okay. Question 7 and 8. A 0.1 kilogram block is attached to an initially unstretched spring, a force constant or a spring constant, 40 newtons per meter. The block is released from rest at time t equals 0. What is the amplitude in meters of the resulting simple harmonic motion? Now you can do this with two ways. You can do conservation of energy, or you work around the equilibrium position, right? Okay, you find your where your equilibrium is, and that's going to be your amplitude basically, because you're always oscillating around the equilibrium position. Okay. Okay, so if I drop it here, and let's say it goes all the way down to here, and this is where it's starting from, right? Just guessing this. Okay, so up here, okay, it's going to stretch by an amount x. Up here, it's got all gravitational potential energy. When it's down here, it's 1/2 k x squared. Now that's maximum stretch. So the amplitude is half of that because you're oscillating around that. Okay, so this is your equilibrium. So I think we can get rid of that. So x is equal to 2 times 0.1 times 10 over 40. So that's going to be 20 over 40. Let's see. Yeah. So it's 1 over this is missing something here. Okay, this is mg. So it's 1 over 20. What am I doing? Yeah, 1 over 20, right? So the amplitude is half of that. Okay, so it's 1 over 40. Another way you could do this is just say, you know what? The equilibrium happens when mg equals kx. And this x here is the amplitude, basically. Okay, so this is going to be 0.1 times 10 equals 40 times x, and x will just be 1 over 40. Okay? What will be the resultant period be? Okay, so let's see. T equals 2 pi square root of the mass over, okay, so this is going to be 2 pi, 1 over, I guess, 400. So this is going to be 2 pi over 20. So the answer is C, so pi over 10. Okay, I'm going to look at RT2. Okay. Okay, so we're trying to rank the frequency. Now, frequency is 1 over 2 pi k over m with a radical. Okay, so if we want to rank the frequency, we just have to rank the ratio of k over m. We don't even have to do the square root. So this is going to be basically 5 over 1. This is going to be 5 over 2. This is going to be 4 over 5. And this is going to be 1 over 1. So the greatest looks like it's, so it's going to be in this order, A, B, D, C. Okay? And the amplitude doesn't matter. We talked about conceptually why the amplitude doesn't show up in the frequency. And the and the period formulas. Okay. A mass attached to a spring oscillates with a period T1. Another oscillator consists of a mass 3 times as much and a spring whose constant is half as much. Okay. What is the ratio of the period of the oscillator, of the oscillators, T2 over T1? Well, T2 equals 2 pi square root. Well, the mass is, so if T1 is 2 pi square root of m over k. So this is going to be 3 times the mass and half the k. So this is going to be 2 pi square root of 6 m over k. So I think I can stick out the 6 outside. Okay, so basically I can see from here that T2 is radical 6 times T1, which is right here and it's sitting there, times T1. So T2 over T1 is radical 6. A block of mass 3 kilograms is attached to a spring whose force constant is 15 newtons per meter. When the block is set into oscillations, how many oscillations does the spring complete? In 10 seconds. So I think we have to find the frequency and just multiply by 10. Frequency is 1 over 2 pi radical k over m. So it's 1 over 2 pi radical 15 over 3. And the answer will be 0.36 hertz, meaning like that's how many oscillations you do in 1 second. So in 10 seconds, you're going to do 10 times as many, so which is about 3.6 oscillations. A spring is hung vertically from a ceiling. A block of mass m is hung from spring, causing the spring to stretch at distance d to equilibrium. Okay, so basically it's like this. It was not stretched, now it's stretched. This is x. A student pulls the mass an additional xo. Okay, what is the spring constant in the spring in terms of m, x, and xo? So I think we can say, okay, mg. I don't know if it's the same question I have here. Yeah, I have a different question, but anyway. mg equals k times x. Should we do this with energy? So I think we can just say k is mg over x, basically. Yeah. That's it. Yeah, the question I have here is different. Okay. So I don't think xo is going to show up because we can just do it with mg equals kx, because when you hang it on it, yeah, it stretches a distance x. So there will be no xo in there. Once released, how many seconds does it take for the mass to reach its equilibrium position, again in terms of x and xo? Okay. T equals 2 pi square root of m over k. So the time that it's going to take is going to be 1/4 of that. Okay. That's going to be pi over 2 square root of m over, I think that xo is just a distraction. K is mg over x. So I think we can get rid of the mass. So this is going to be pi over 2 radical x over g. That's what you have in your in your answer key. Number 12. Okay. Okay. So I think from the first part, I think we're going to get the K. Okay, so mg equals kx. So this is 20 equals k times 0.1. So the k is 200 newtons per meter. When it's sitting on the incline, these two forces are equal. So I think mg sine of theta, 45, is equal to kx. So this is going to be 20 sine 45 equals 200 times the new x. So x is going to be equal to 0.7, or if you change it to centimeters, it's going to be 7.07 centimeters. The answer you're going to get should be in meters, and you can change it. What is the period of the oscillation motion that the cart would undergo on the incline compared to the hanging vertically? I think the period will be the same, okay? And that's going to be t equals 2 pi square root of m over k, which is going to be 2 pi. That's going to be over 10, so it's going to be pi over 5 seconds. I think, and it should be the same whether it's on the incline or vertically, because the acceleration of gravity doesn't really matter. So yeah, it's on the incline, it's a weaker gravity, but it doesn't matter. The formula for t doesn't even show the acceleration of gravity, and we discussed the reason why in class. So I'm not going to talk about it now, so that you learn to listen in class. Okay. An object, so this is simple harmonic motion that varies with time. Okay, so this equation here is also a cosine 2 pi f times t, and it's also a cosine 2 pi over period times time. Okay, what is the frequency? Well, all I have to do is match, really. 2 pi f should match up with 2 pi over 3. And if we do the math correctly here, we get 1/3 hertz. What is the amplitude? Well, there are no numbers here, so the amplitude is just basically A. What is the period? Frequency is 1/3. Period is the flip of frequency, so that's just going to be 3 seconds. What is the first time after t equals 0 that the object reaches equilibrium? So basically, when you reach equilibrium, x is 0. So I think we have to say a cosine 2 pi over 3 t equals 0. Okay, that's not what's making it 0. So 2 pi over 3t should equal pi over 2, because that's when the cosine is equal to 0, at pi over 2. So the time should be 4/3 of a second. Or 3/4. 3/4. Another way we could have done this, we could have just said when it reaches the equilibrium, that's 1/4 of a cycle. So we just take the period and divide it by 4. Probably that would have been easier. Okay. Okay, so we're going to write the equation of this. Now, this is not a cosine function. This is more like a sine function, but it's flipped. So it's negative n sine of 2 pi over the period looks like it's 4n times t. So I think if we clean this up a little bit, sine of pi over 2n times t. Let me see if that's what I have. Yep. At what time does the mass have the most positive velocity? I think the velocity is greatest and positive here, because that's the greatest positive slope. So this should be at 2n. Okay, what is the value of n in the graph? N is just a quarter of the period. Okay? Yeah, n is just a quarter of the period. So I guess I can just say n is quarter of t. At what time does the mass have the most negative acceleration? So we know that displacement and position or displacement and acceleration are always opposite. We learned that earlier in the unit, and we explained why. So the maximum, the most negative would be at 3n, because that's when the displacement is at maximum and positive. We're looking at number 15. Okay, we want to have maximum negative velocity. That's going to happen here. That's the steepest part of the curve, and it's negative slope. So it's going to happen at B. At what time does the object achieve maximum positive acceleration? That should be at point C, or at point that's equivalent to C. Yeah, because that's when the displacement is maximum and negative. So that's where the acceleration will be maximum and positive. Right. All right, for 16, I'm going to rewrite the equation as 3 cosine 2 pi f times t, 3 cosine 2 pi over t times t. So I can see my variables in there. What's the fastest speed? In order to get the fastest speed, I think we have to do conservation of energy. All right, so I'm going to find the k first. Yeah. Okay, so t equals 2 pi square root of m over k. Okay, and I think the t in here, and also t is equal, or 2 pi over t is equal to 2, which means t is pi. So here I got to bring in pi and put in, and solve it in here in this equation here. So I can divide by that. So 1/2 equals radical m over k. If I square both sides, I should get 1/4, and then I should get k equals 4m. Now I'm going to do conservation of energy. The maximum velocity happens at equilibrium, where there is only kinetic energy. Okay, and zero kinetic energy happens when you are all the way fully stretched or fully compressed. So this is mv square equals 4m based on that. A is going to be 3 square. So V will just be 6 meters per second. The greatest acceleration, I think we can just do A equals negative omega squared times x, which means A equals negative k over m, k over m times 3, but technically it should be negative 3, okay, because, well, actually it doesn't matter. We can do 3 or negative 3, just looking at the magnitude, basically. So this is just going to be 12 meters per second squared. Another way we could have done it is say F equals ma. Okay, so this is 4m, this is 3, this is m times a, and you get 12. All right, for this one it says what is the mass m in terms of lowercase m. So if the period is 3.5 times as much, here. If the period becomes 3.5 times, it means the mass has to become 9/4 as much. So 9/4 of the mass that you have is equal to what you had plus whatever you added. Okay, so just doing proportions here. So m is equal to 5/4 m if you solve the math here. Okay, if you don't like that, you're going to say, well, t is 2 pi square root of m over k, but 3/2 of t is equal to 2 pi square root of m plus the additional mass over k. So you can do this in a lot of ways. You can just take this and put the t in there. And you can cross out a lot of stuff here. Okay, you can square, you get 9/4 equals 9/4 m equals m plus m, and that's what we established earlier. So if you can do the proportions, it's much better, much quicker. What is the system speed v through the equilibrium position with the additional mass placed in place? In terms of v and the two masses, well, 1/2 k a square is the total energy. That's equal to 1/2 mv square, but also is equal to 1/2 m plus big M, some new velocity square. So if we set these two equal to each other, we get big V equals radical this ratio here times small v on the outside. So I'm going to put it here. So if I put it there, you might think it's on the inside, which makes some sense because there's more mass. This has to be slower to have the same energy. A spring mass oscillator consists of a spring of constant 10 newtons per meter and mass 2 kilograms. The amplitude of the oscillator motion is 0.3. What is the mechanical energy? So we're looking for the total energy here. So basically it's 1/2 k a square. So it's 1/2 times 10 times 0.3 square, and you're done. So it should be 0.45 joules. Which of the following is true? The kinetic and potential energy are equal to each other at all time. Not true. And a counter example is like in the middle at equilibrium, kinetic energy is maximum, potential energy is 0. The kinetic and potential energies are both constant. That's not true. Kinetic, we're speeding up, we're slowing down, so the kinetic energy changes. The same thing with potential energy, we're compressing, we're stretching, so the potential energy changes. the maximum potential energy is achieved when the mass passes through equilibrium. That's not true. That's true for the maximum kinetic energy. The maximum kinetic energy and maximum potential energy are equal, but occur at different times. Yeah, sure. Okay. Okay, because the maximum kinetic energy happens at equilibrium, maximum potential energy happens at maximum stretch / compression. All right, I'm going to continue with the simple harmonic motion from page 13, and then we're going to talk about the energy stored in the spring, or the energy of the whole system, including the object. Now here, this is elastic potential energy, that's energy in the spring. When you're all the way at the end, either at A or negative A or A, all your energy is in the form of elastic potential energy. When you are in the middle, there is no more stretch or compression, so all your energy is kinetic. But anywhere in between, you have both types of energy because you're moving and at the same time, you either stretch or compressed. So let's look at the different parts of this trip here. So if you are at negative A, assuming you started from A, after half a period, you're going to find yourself at negative A. So if you're at negative A, all your energy is in the form of potential energy. If you are at 0, all your energy is in the form of kinetic. If you go back to A, it's in the form of potential energy. And you can read the rest of this page, and you're going to see the different types of energy at different locations. Right. Here it says, in order to find the maximum speed, meaning in the middle, I think all you have to do is work between these two equations here, these two expressions, and you're going to see that you can isolate Vmax, and if you get rid of the halves, you divide by m, and you take a radical, you should get Vmax is A times radical of K over m. Okay, so that's something that should be easy to do. All right, so I'm going to do some energy bar charts. And what I'm going to do actually here, I'm going to do it at different places. So I'm going to do it at position, either A or negative A, okay, at either one of those. So at position A, all my energy is potential. So this is U. And this is no kinetic here, kinetic energy. Okay, now let's see what happens at 0, in the middle, at the equilibrium position. It should look like this. There is no elastic potential energy because you are not compressed or stretched, and all that energy you had up here is in the form of kinetic energy now. And let's look at some other special cases. Let's say at A over 2 on either side, so plus or minus A over 2. So at A over 2, so I'm going to do 1, 2, 3, 4, 1, 2, 3, 4. Okay. At a over 2, because of the square on top of the x square, you only have a quarter of this energy here. So you should only have 1 bar for elastic potential energy. And the other 3 bars should be in the form of kinetic. Okay? So this is your kinetic energy. Okay. Now, the other thing we can try is, like, we can try to figure out a place. I mean, this is not drawn to scale, but you got the idea. Okay? 3 bars. In other words, this 3 added to that one should equal to that height over there. Now, let's try a location where okay. Let's try a location where U is equal to kinetic energy in terms of A. So at this location, I have 1/2 k x squared. I'm going to find the x here, right? Plus, I can do 1/2 m v squared equals 1/2 k a squared. Okay, and I'm setting it up so that my potential energy and my kinetic energy are the same. So I'm basically saying this, that this 1/2 mv squared is just 1/2 k x squared. So we can do something like that. So we have 2k x squared is k a squared, which means x is equal to plus or minus a over radical 2. So at this exact location on either side of the equilibrium, your elastic potential energy and your kinetic energy have to be the same. So if we go back to the bar chart, we should have 2 segments for each. So this is your potential energy and this is your kinetic energy. You can do this for, you can say, well, I want to find a place where my elastic potential energy is half of my kinetic energy. So let's see what we can do. So let's see. So we're going to do 1/2 k x squared, and you want your this here to be half of the kinetic energy. So basically, you want your kinetic energy to be twice as much. So you want it to be twice that. Equals 1/2 k a squared. I hope that makes sense. Okay. So U has to be half of the kinetic energy, which means the kinetic energy has to be twice as much as that. So if we can do this, we can maybe get rid of these k's. So let's see what we have here. So we have 3x squared is a squared. So x is going to be equal to plus or minus a over radical 3. And you can do this for all possible scenarios. All right. I'm going to try to make this smaller so we can fit everything in there. Okay. So the function here is x equals a sine omega t. Now keep in mind that this position time graph can be a sine or a cosine. It all depends when the time starts. So if you're trying to do the velocity here, it looks like the velocity starts positive because this slope is positive. So, and its maximum here, that's the steepest part, and it gets to 0, right? And then it gets to maximum steepness but negative, and then it gets back to 0, and then here it gets to maximum steepness and positive. Okay, so my curve should look something like this. Should look like a cosine function. if I do the acceleration, it's also going to be a sine function. It's going to be the same function as x, except that it's going to be flipped. And I think we've learned that before. So it's going to be upside down x position. Now, these maximum values for v and for acceleration are not the same as the maximum values for x. And we talked about that, and I showed you how you can find those. All right. For elastic potential energy, this has to do with x squared, so it's going to follow. Here you have no elastic potential energy. When the speed is 0, you have maximum. When the speed is at the equilibrium, the speed is maximum, right? So you have no elastic potential energy. In here, so now elastic potential energy is 1/2 kx squared, so it has to remain positive. In here, you have no speed, so which means you have maximum elastic potential energy, and here you have no stretch, so which means you have no elastic potential energy, and your curve should look like that. Okay. All right. Here it should look more like that. Okay. Now the kinetic energy is just going to be the opposite of that, because the total energy has to remain constant at this value. So this one is going to look like that. Okay, so it's just going to be the flip. Okay. Let's go back to our normal size. Okay. For number 21, an ideal spring is attached to one end of a wall and the other end to a mass M. The mass is set into oscillation along a frictional force by okay. So we're trying to find the k here. So I can say that 1/2 k x squared, which is really a squared, is 1/2 m v maximum squared. So I can get rid of that. If I want to find k, all I have to do is divide this by a squared. So the answer should be D. Let's look at 22. A mass is attached to a spring with a spring constant k. If the mass is set into simple harmonic motion by displacement d, so instead of saying x, they called it d, from equilibrium, what would be the speed of the mass when it returns to equilibrium position? So here we just have to do 1/2 k d squared, that's your amplitude, equals 1/2 m v maximum squared. So v is equal to d, I'm sorry, I crossed out the wrong thing, d radical k over m. So the answer should be D. Okay. For number 23, you're going to pull on something, right? Yeah, it's pulled at distance d. When released from rest, the block moves towards equilibrium. What coefficient of kinetic friction between the surface and the block would allow the block to return to equilibrium and stop? So we're going to do conservation of energy. Initially, I had all elastic potential energy the moment I released it, right? Okay. Plus, there is some work done by friction, and at the end, I ended up with nothing. It's not stretched because it's at the equilibrium, and it's not moving. So if I want to find now the work done by friction, if you remember, is mu mg times the distance that it's going to travel. Well, it's going to travel at distance x, cosine of 180. Okay, so here I think we can just clean this up a little bit, get rid of one of the x's, and say 1/2 kx equals mu mg, and mu is equal to kx over 2 mg. So the answer is C. All right, let's look at 24. An object is attached to a spring and oscillates with amplitude A, period T. The nature of the velocity v and acceleration of the graph at time is best represented by which of the following? So at a quarter of the period, you are here. So this is T over 4. Okay. At that moment there, your velocity is 0 because the slope there is 0. And the acceleration has to be negative because we learned that the graphs of displacement time and acceleration time are flipped. Right? So we have to be here at D. Okay. All right, let's look at this RT3. All right, so they're giving us this first experiment A, and they're making some changes, and we're going to see what could have changed. Okay. Compared to experiment A, in experiment B, the cart has, well, let's see. I don't think the mass changed. See, the period remained the same, right? So here is one period, and here is one period. So the period remains the same. So since it's the same spring, okay, so T equals 2 pi square root of m over k. If the T stays the same and k stay the same, m has no choice but to remain the same. Okay. Compared to experiment A, experiment C, in experiment C, the cart has, well, let's see. So let's take a look at experiment C. In here, the period stops there, but the period for the other one is kind of like there-ish. No, it's here. Period of the other one is here. Okay, so it looks like the period here is just half as much as it was up here. So in order for the period to be half as much and the spring constant is the same, if you want to get half of that out here, you have to make the mass 1/4 as much. Because when you take the square root, you have to come out with a half. So the mass has to be 1/4 as much. Okay, there's an experiment D. The mass used in experiment A was doubled, and the spring was replaced with spring constant 2k. The period in experiment D would be, it should be the same, because if you double the mass and you double the k, you pretty much did not do anything. Okay. Now let's look at RT4. Okay. So the first question, what is the period of the motion of this cart? Well, the period is just 8 seconds. I mean, you just have to read from the graph. You just have to see one cycle. As soon as you start to repeat, you stop and you read that number. So it's 8 seconds. What is the frequency? Well, the frequency is just the reciprocal of period. So your frequency will just be 1 over period, 1 over 8. Okay. In which direction was the cart displaced from equilibrium before it was released? Well, it had to be pushed in to the left, because when it first started, it had a positive velocity, which means when it first started, it started moving to the right. So it had to be pushed to the left, because if you pulled it to the right, when you release it, it will have a negative velocity, and this whole thing will be flipped. A mass is oscillating up and down at the end of a spring. 3 students are discussing the acceleration of the mass. Okay, Eileen says, I think the acceleration will be largest when it is at the end of its oscillations turning around. That's where the spring is stretched the most. That's true, because that's when you have the maximum force, okay? And force is directly proportional to acceleration. So when you have maximum force, you must have maximum acceleration. So she's right. Okay, let's look at the other people. No, I don't see how that can be. Its velocity is 0 at that point, so its acceleration has to be 0. That's not true. If the velocity is 0, the acceleration is not necessarily 0, and I think we used the example of throwing something up in the air. At the very top, the speed is 0, but gravity does not take a break. Gravity is still acting on it. Okay, because if the acceleration was 0 at the top, it will just stop there. Okay. I disagree. The acceleration is largest when the mass is halfway between the middle and the end, because it's where the speed is changing the most. That's not true, because in the middle, the acceleration is 0 because there is no stretch. So Eileen is correct. Okay. A mass spring system consists of a spring with a spring constant of stiffness K and an end stretch length L, connected to a cart of mass M resting on a horizontal frictionless surface. If the cart is pulled to one side a small distance and released, it will oscillate back and forth with amplitude A and frequency F. Okay, this is all stuff we know. Okay. Identify from choice. Okay. How each change described below will affect the frequency of the oscillating mass spring system. Compared to the case above, this change will. Okay. Okay, so we're looking at, the mass is increased. So now we have to write the formula. T is 2 pi square root of m over k, and frequency is the flip of that, or the reciprocal. Okay, so if I increase the mass, so if I increase the mass, the frequency has to drop because there is an inverse relationship between mass and frequency. Okay, the spring constant of stiffness is increased. So if I increase K, there is a direct relationship between F and K. F will increase. The mass is pulled a little further and then released. So we're changing the amplitude, and we explained in class that the amplitude does not affect the period, and consequently it doesn't affect the frequency. Okay, the spring constant is double and the mass is reduced to half. Well, if you multiply the K by 2 and you cut the mass in half, so you basically introduced a factor of 4 inside the radical, which means a factor of 2 outside the radical. So the frequency will have to double. The amplitude is increased and the mass is increased. Well, if you increase the amplitude, that has no effect. But if you increase the mass, it's just like previously the frequency will have to decrease. Okay. Now we're at RT7. A mass hanging on a vertical spring is pulled down at distance d and released. The mass undergoes simple harmonic motion. The 3 students make the following contention about the situation. Okay, Alexandra. The maximum kinetic energy of this mass spring system is fixed by the properties of the system and does not depend on how far down the mass is pulled. Well, that's not true, because if you pull, if your amplitude is bigger, if you pull more, which means you put in more work into the system, there will be more elastic potential energy stored, which will eventually, when you are halfway at the equilibrium position, will all become kinetic energy. So it depends on how far down we pull. It depends on the amplitude. All right, the next person. No, that can be right, since increasing the amplitude or how far down it is pulled increases the potential energy of the system. I don't think the amplitude has any effect on the on the frequency. Well, we have no that's true. The amplitude has no effect on the frequency. I agree in part with both of you. I think the amplitude does affect the maximum kinetic energy, but also I think it affects the frequency of oscillations. No, the amplitude does not affect the frequency, but it does affect the kinetic energy. Let me see what Bruno said. No, that can be right, since increasing the amplitude or how far down is pulled increases the potential energy of the system. Oh yeah, Bruno was right, because I read this as the amplitude has an effect. Yeah, so the amplitude has no effect. So Bruno is the one that's correct. Okay? Yeah, because the more amplitude, the more energy is stored in the spring, and the more kinetic you're going to end up with. Yeah. Yep. Okay. All right, let's do this energy bar chart. Okay. At point A, we have to turn around. So there's no kinetic energy, and our potential energy is 4 bars here. Okay. At point B, which is halfway the maximum displacement, because of that x square, we should have, at the halfway mark, we should have a quarter of the potential energy. So a quarter, so 1 bar is elastic potential energy, and 3 bars have to be the kinetic energy. And here at point C, there is no stretch, which means you have nothing here. At point D and point B are symmetrical, right? So it should look the same. And point E should be exactly the same as point A. Okay. So just keep in mind that when you're halfway, the maximum displacement, a quarter of your potential energy is, a quarter of your total energy is potential, and the other 3/4 are kinetic. All right, let's look at RT9. A cart attached to a spring is displaced from equilibrium and then released. Okay, so they're giving us a displacement versus time graph, no friction. Okay. Okay. At which point or points are the spring potential energy and the cart kinetic both at their maximum value? They can never be at a maximum value at the same time, right? Because when one is maximum, the other one is minimum. Okay. At which point or points is the kinetic energy equal to 0? Well, it's equal to 0 when it stops and turns around. So it should be points A and E. At which point or points is the total energy at its maximum value all the time? Because we're talking about total energy, and total energy stays constant no matter where. Okay. At which point or points is the spring potential energy negative? It's never negative because of that x square. So both kinetic energy and potential energy are both positive. Okay. Energy is a scalar quantity, so we can't talk about the negative part of energy. Okay. At which point or points is the kinetic energy positive? Well, it's going to be positive whenever it's not 0, right? So it's going to be positive at B, C, D, F, and H. And G, right? Because it's still moving at G. At which point or points is the kinetic energy at its maximum value and the spring potential energy that is at minimum value? So the potential energy is at minimum value when there is no stretch, okay, which means C and G. And if that's it, if the potential energy is at minimum, the kinetic energy has to be at maximum. You can also look at it as the speed at C and G is maximum because that slope or that segment is the steepest, okay, in those areas. At what point or points? At what point or points is the kinetic energy minimum and potential energy maximum? Well, kinetic energy is minimum at A and E because it's not moving, and potential energy is maximum at those points because that's where you have maximum stretch or compression. And that's it.